Today we're going to look at quadrilaterals. Quadrilaterals are four-sided shapes. Quad is Latin for four, and quadrilaterals also have four interior angles where their vertices meet. Quadrilaterals can either be convex, so all of their vertices point outwards here, or they can be concave, where one vertex points inward. So here is a vertex that's pointing inward, all the others are pointing outwards, out of the shape, but in a convex, all of the vertices point outwards. We can remember which one is a concave because our concave bends in like a cave would, inside into the cave. We can have a look at some properties of special quadrilaterals now and have a look at the angles and side lengths and the relationships between them. So firstly, having a look at a square. Our square has all sides the same length. Also, all of the angles inside a square must be 90 degrees, so they're all at right angles to each other. If we were to look at the diagonals, these red lines here, and drawing the diagonals in, where they cross, where they intersect right in the centre here, the angle that they intersect at is 90 degrees as well. So each of these angles inside where the diagonals intersect each other is 90 degrees. We also see that each of the diagonals is split evenly in half. So this length here is the same as this length here, and this length here is the same as this length here. So the diagonals are both equal in length, and they're cut in two by the intersection of the two diagonals in the centre. In our rectangle, there's a couple of differences between the square and the rectangle. The main difference is that the side lengths aren't all the same, but the opposite sides are the same length. So this length is the same as this length, and this length is the same as this length. Once again, just like the square, the interior angles are all right angles. When we draw in the diagonals though, they do not intersect at right angles. In the centre here, they do not intersect at right angles. They do, however, just like in the square, cut and intersect so that each of the diagonals is cut in two. So this diagonal here is cut in two as well as this diagonal here. So it means that each of these lengths are all the same. If we look at a parallelogram now, a parallelogram is like a rectangle that has been squished or moved to the side. So we have the same property where the opposite sides are the same length. And so these two sides are the same length here, as well as these two sides are the same length. Our opposite sides are also parallel, so they're denoted by our parallel lines here. If we were to have a look at the angles inside the parallelogram, the opposite angles are equal. So the opposite angles are equal here. We can also see that each of the diagonals is cut in two, but the diagonals aren't the same length. So the rectangle, this length is the same as this length, but in our parallelogram, this length here is much longer than this length here. A rhombus is very much like a square that's been squashed, so it's similar to a parallelogram as well in that the opposite angles are equal. Okay, so these angles are the same as these angles. It's different from a parallelogram in that all of the sides are the same length. All opposite sides are still parallel. These opposite sides are still parallel. Where our diagonals intersect is at a right angle as well, just like our square. And like our parallelogram, our diagonals are cut in two. So this diagonal here is divided exactly in two, but this diagonal here is much shorter than this diagonal here. For our kite has these two side lengths the same and these two side lengths the same. It also means that if we draw our diagonals, they intersect at right angles. Only one of the diagonals will be cut in two though, the other one is cut unevenly. And that's pretty much it about kites. Trapeziums, the only thing we can say about trapeziums is that two of their sides are parallel. That's the only thing that we can say definitely about trapeziums. With any quadrilateral, however, the sum of all the interior angles is 360 degrees. So if I was to have our quadrilateral here, and I was to add A plus B plus C plus D, that would all equal 360 degrees. If we want to use that fact to solve a problem, then we can use a code of reason like this that shows a quadrilateral and all of the interior angles of the quadrilateral. So that all of those interior angles add to 360 degrees. So let's do some examples now. We need to find the value of pronumerals in these quadrilaterals. So firstly, we've got a parallelogram here. We know one angle is 77 degrees and we're trying to find the other angles. So 77 degrees and our A degrees here, we know they're co-interior angles. There are two parallel lines here, intersected by this transversal, and they're inside, both inside the parallel lines and the transversal. So in order to do that, well, we know that co-interior angles add to 180 degrees, so A plus 77 must be 180. In order to make that true, A must be 103. So A is 103 degrees here. If we then have a look at these two angles being co-interior, A and B being co-interior to these two parallel lines, and this line here being the transversal, then that means that B plus A must be 180 degrees as well. And we know that A is 103. So B plus 103 is 180, using the co-interior angles, so B must be 77 degrees as well. We also know that the opposite angles in a parallelogram are equal, so B must be equal to 77 degrees, and we can see that that's true there. For our last example here, we've got a quadrilateral with four different angles. One's 90 degrees here, so this angle's 90 degrees there. One angle's 100 degrees, one's 115, and the other one we need to determine C. So we know if we add all of those angles together, they'll equal 360 degrees. And we've shown our coded reason there that all of the angles in a quadrilateral add or sum to 360 degrees. 100 plus 115 plus 90 is 305. So C plus 305 equals 360. The only value for C that can make that true is if C is 55. So here, our angle here is 55 degrees.